This example is going to compare two ways of representing the DC to AC converter in the IVR. The first is the average model, which is going to produce smooth AC voltages. The power plant controller in the regulating controller are going to produce reference phase voltage waveforms that can be, on a per unit basis, described as MA, MB, and MC over here. These are going to be sinusoidal, 120 degrees out of phase. And the derivation of this, you can look in the book by Yazdani and Yeravani, the one on voltage source converters for power systems. So when we have these modulation indices, you can control a voltage source according to that modulation index times the DC voltage over 2. So the maximum voltage, if the modulation index is 1, the maximum voltage is going to be VDC over 2, because there's going to be a midpoint in the DC bus, and so half of that can be applied from neutral to the phase voltage terminal. Each phase has a controlled voltage source, the diamond shapes here, connected to phases A, B, and C, and they're going to inject currents IA, IB, and IC into the grid. To get the effect on the DC side, there's a controlled DC current source over here, and it is constructed this way. The modulation index times the AC current for the corresponding phase, all added up and divided by 2. You can check the power balance, that the power is conserved by double checking that equation, and you'll see there's no losses or no energy gained inside that converter, and you'll see if the modulation indices are sinusoidal, as a controller should generate them, you're going to generate sinusoidal voltages, so no harmonics. So that was the average model. The other way to model the converters with the switching model, or in one of the tools they call it the detailed model. So you take the same reference modulating signals, MA, MB, and MC, and whenever that is, those signals are above a carrier frequency, you're going to generate a positive firing pulse. So for example, when MA is bigger, in magnitude than the carrier, we close that switch. And whenever SA isn't closing that switch, we have to close the switch, the complementary switch connected to the negative DC terminal, so that we have a path for the current to flow in all three phases at all times. The switching model allows us to put in the snubbers, the RC snubbers and the diode, and sometimes there'll be an inductor in there in parallel with each switch. So we're going to get some more of the transient effects across each switch, and also losses and some harmonics. So this frequency, this carrier frequency in black, the triangular waveform, that is, I believe, 360 hertz, just for, so we can visualize it. But if you look, let's take the green one, since my highlighting is in red. Right there, whenever the green waveform, that's modulating index for phase B, is above the carrier, instantaneously that reaches a positive +1 to turn on this switch over here. And whenever that firing angle, that firing pulse is 0, then this switch is going to be turned on. So this is going to turn the voltage source. You can think of it as a voltage source being turned on to that AC phase terminal just for intervals. It's either on or off, and what that is going to do is generate non-sinusoidal, or well, they're sinusoidal but with harmonics, and so we'll see a difference in the current waveforms, especially when we use the average model or the detailed model. Typically, the carrier frequencies are higher than are shown here, so we've got to run with a smaller time step, 10 microseconds, maybe even less. With the average model, we can typically run even up to 50 microseconds or higher if we're pushing it. So there's a big difference in simulation time, but we do lose some detail with the average model.